Hello, my name is Steve Miller and I'm the Technical Marketing Manager for the Simscape product family at MathWorks. In this presentation we're going to see how you can model physical systems using Simscape. Here are the key points for this presentation. First, we'll see that Simscape enables you to use physical networks to model systems spanning multiple physical domains. The component models in Simscape have physical connections. This enables you to model physical systems by assembling a physical schematic. This is different than the input-output connections that you may be familiar with from Simulink. Next, we'll see that Simscape provides a MATLAB-based language for creating custom component models. The component models in Simscape are defined using the Simscape language. This language is based on MATLAB, and you can use it to create your own physical components and define custom physical domains. Next, we'll see that Simscape add-on products can be used without requiring extra licenses. The Simscape product family consists of a platform and add-on libraries. Your model developers can create models that use the add-on products and the platform. To share these with other users, they can save it in restricted mode. The other users can use this model without requiring licenses for the add-on products for tasks such as parameter testing and C code generation. Here is the agenda for our presentation. First, we'll look at our example application, which is a hydraulic lift with an electronic control system. We'll build up a portion of that model by assembling components from the Simscape Foundation library. We'll customize one of those components using Simscape language. We'll then enhance the model, adding additional effects using components from the Simscape add-on libraries. We'll also show how you can share this model with others who don't have those licenses using Simscape editing modes. Next, we'll log some simulation data and use that data to detect the cause of a slow simulation using the Simulink Solver Profiler. And finally, we'll see how we can configure the model to simulate in real time for tasks such as hardware-in-the-loop testing. Simscape is used for a wide range of applications. We will look at a model of a hydraulic lift. Our hydraulic lift has an electronic control system that controls the motion of a servo motor. The servo motor provides linear actuation that moves the spool in a hydraulic valve. The hydraulic valve controls the flow to and from a double-acting hydraulic cylinder. As that cylinder extends and contracts, it raises and lowers a load on a scissor jack. Simscape is used to detect integration issues between the different systems, to optimize system-level performance, and to design and test control systems, including hardware-in-the-loop testing. I'll now switch over to the model so you can see how this is done. Here is the model that we're working with. A hydraulic cylinder extends and contracts to raise and lower the load on a scissor jack. When we run the simulation, we'll see how well the system tracks a reference input. The yellow line on the scope is our reference input. We can see that the measurement from our system, the pink line, tracks the reference signal quite well. Here you can see a three-dimensional animation of the scissor jack. This animation is produced automatically from the simulation results by Simscape Multibody, an add-on to Simscape. You can see that as the cylinder extends and contracts, it raises and lowers the load. The control in our model is modeled using an electrical circuit. This electrical circuit has been created by assembling components from the Simscape Electrical Foundation library, such as op-amps, resistors, and capacitors. Using these, we have created a summing amplifier and a proportional integral controller. This is used to control the servo motor. When we go into the servo motor model, we can see the electrical and mechanical components that model the servo motor. The current controller for our motor has also been modeled using Simscape electrical components. The rotational motion of the servo motor shaft is converted to a translational motion using the wheel and axle. The translational motion provided by the servo motor controls the movement of a spool in a hydraulic valve. As the spool moves back and forth, it opens and closes different hydraulic passages. This connects the pressure from the pump to the A port or the B port of our valve. These ports are connected to the hydraulic cylinder. As the valve moves back and forth, opening and closing those paths, hydraulic pressure is applied to one side or the other side of the hydraulic cylinder, allowing the cylinder to extend or contract. These mechanical connections are connected to our three-dimensional mechanical model of the hydraulic jack itself. This is the model that has been created using Simscape Multibody, where this animation comes from. Here you can see the different mechanical parts and the joints that define how the parts move with respect to one another. Important to note is that all of the connections that you're seeing on this diagram are physical connections. These represent the physical connections between the different physical components in our system. It enables a bidirectional flow of energy between the components. This is different than the input-output connections that you may be familiar with from Simulink. Now that we've seen an overview of our hydraulic lift model, let's take a look at the different modeling methods available in the Simulink environment. Using Simscape, you can create physical networks within the Simulink environment. Simulink is best known for signal-based modeling. This is also referred to as causal or input-output modeling. To explain this approach, we'll look at an RC circuit. An RC circuit implemented using an input-output approach is a transfer function. A transfer function will accept a numerical input, apply a mathematical operation to it, and calculate an output. This is different than models based on a physical network. With Simscape, you connect components using physical ports. These physical ports enable a bidirectional flow of energy between the components. What this means is that Simscape can determine the system-level equations for you. To see the power of this approach, we'll look at a more complex physical system. If we add a second RC stage to our RC circuit, this is what the input-output model looks like. It's not quite the same as simply copying and pasting the transfer function. We have to rederive the equations, taking into account the impact of the second RC stage on the first RC stage. Using a physical network approach, we can simply copy and paste the first RC stage. Simscape will determine the system-level equations for us. Using Simscape, the system-level equations are formulated automatically, they are solved simultaneously, and this approach can be applied to multiple physical domains. Both the input-output approach and physical network modeling methods are available in the Simulink environment. Now we will assemble a portion of our hydraulic lift model. We will connect together Simscape components to create a model of a DC motor. In this demonstration, we're going to see how we can use Simscape to model a DC motor. The system we wish to model looks like this: a DC motor that has 2 electrical connections and 2 mechanical connections, including one connection that can translate along an axis. We wish to model this system with electrical and mechanical effects. We will use Simscape to model it. The model we build will look like this, and when we run the simulation, we will see how the motor reacts as it acts against a spring. We'll use the MATLAB command sscnew to open up a new Simulink model. Using the command sscnew opens up a Simulink model with the settings recommended for Simscape models. It also adds a few of the blocks commonly used in Simscape. To model our DC motor, the first thing that we'll need is a DC voltage source. I'll click in the diagram and type in DC voltage source, and then select the component from a list. I'll set the voltage to 5 volts. The next thing that we'll need is a resistor. I'll click and drag to create an electrical connection, and then type in resistor, and then select the resistor component. We then need a block that will convert between electrical and mechanical energy. I'll type in electro, and then select the rotational electromechanical converter. I'll then connect this to our resistor. Our electrical circuit will also need an inductor, which will then connect to the other side of our converter. We'll also need a ground block. So I'll type in electrical reference and connect it here. Simscape uses solver technology above and beyond what's available in normal Simulink. To have access to some of those settings, we'll connect the solver configuration block. The next thing that we'll do is the mechanical portion of our model. These 2 ports represent the mechanical connections of our motor. We'll attach the housing of the motor to a point fixed in space. We'll insert a mechanical rotational reference block. This connection represents the shaft. I'll click and drag to create a mechanical connection, and then insert an inertia to represent the inertia of the shaft. We want to model the viscous friction in the bearing of our motor. I will right-click and drag to create a branch, and then insert a damper block. We'll connect the damper to the housing of our motor. We want to convert the rotational motion of the shaft to translational motion. We'll do that using a wheel and axle block. We want the motor to act against a spring, so we'll insert a spring, and the spring will be connected to a point fixed in space. With this, our model is complete. We can run the simulation. I'll right-click on the block and select Simscape View Simulation Data Simlog. Here we can see the Simscape Results Explorer. We can explore the results of our simulation through this tree browser. Here I can see the speed of the shaft as it settles out to 0 radians per second, and I can look at electrical quantities such as the current through the resistor. We can see how much the spring was compressed by selecting the x variable in the translational spring, and we can see that it compressed to about 0.01 meters or 1 centimeter. I can increase the distance that the motor shaft moves by resetting the stiffness of the spring. Here I can change it to a new numerical value, or I could assign a MATLAB variable. I can also adjust the units, and I can configure this parameter to be a runtime parameter, meaning that I can change this value without regenerating C code. I'll rerun the simulation, reload the simulation results, and we'll see that the spring now compresses 2 centimeters, again because we've halved the stiffness of the spring. If I want to view the results of the simulation on a Simulink scope, I can use sensor blocks. I'll right-click and add a motion sensor. And we'll measure the motion of the shaft with respect to the housing. The sensor block produces a physical signal. This physical signal can be used to implement simultaneous physical equations. We need to convert this physical signal to a Simulink signal in order to view it on the scope. In that conversion, we'll assign the units, so we'll assign it units of degrees. Now when we run the simulation, we can see how much the shaft turns on a Simulink scope, and we can see that it settles at about 22.5 degrees. In this demonstration, we have seen how we can model a DC motor using Foundation Library components in Simscape and analyze the results in the Simscape Results Explorer. Just as we modeled a DC motor by assembling components from the Simscape Foundation Library, we can model components from hydraulic and other physical domains in the same way. Let's look at a hydraulic valve. A hydraulic valve consists of passages that connect the pump port and the tank port to the A and B ports of the valve. You can see the structure here in Simscape. Variable area orifices open and close to connect the pump to the A or B port of the valve. Similarly, other variable area orifices can connect those ports back to the tank. Let's look at a hydraulic cylinder. A hydraulic cylinder can be thought of as two variable volume chambers, the volume of each chamber dependent upon the position of the piston inside the cylinder. Here you can see we've modeled that using Simscape Foundation Library components. Variable volume chambers on each side represent the two sides of the double-acting cylinder. These two components represent the piston that converts the hydraulic energy on both sides into mechanical energy. This hard stop component represents the limits of the piston travel inside the cylinder. Each of these components has been assembled using components from the Simscape Foundation Library. In Simscape Fluids, these blocks are represented by a single block. This same approach can be used on the electrical domain, where we can connect electrical components to assemble filters and other electrical circuits. We can use this for thermal, mechanical, fluids, magnetic, and other domains. I'll now switch over to the model so you can see a few examples. In our model of the hydraulic lift, each of these subsystems represents a physical component, and each of them has been modeled by assembling components from the Simscape Foundation Library. Let's look at the pump and tank. Here we have simply modeled the pump as an ideal pressure source, with the pressure defined as a Simulink input. More complex pump models are available in Simscape Fluids. The return from the system goes to a tank, and this has been modeled using a hydraulic reference. Both of these components are saved in the Simscape Foundation Library. If we go into the hydraulic elements, we can find the hydraulic reference, which we're using to model the tank, and in the hydraulic sources, we find the hydraulic pressure source. You can go through the Foundation Library to explore the other elements that are available, including electrical elements, mechanical elements, and further down we have thermal liquid elements for components or systems where the fluid properties depend on temperature, and two-phase fluids where you have liquids that can convert to gas and then back again. Returning to our model, let's take a look at the valve. In our valve model, we have variable area orifice blocks that control the flow of fluid from the pump port to the A and B ports and back to the tank port. To model a hydraulic valve, we need to convert the mechanical motion of the spool into the area that will define the opening between the pump and the other ports. We do this using blocks from the Physical Signals Library. Here you can see that we are taking the input of the spool, a displacement, and converting that to an area using a lookup table. Though these look like blocks from Simulink with their signal inputs and outputs, there is an important difference. When we model these equations using these blocks, these equations will be grouped together with all of the equations from the Simscape physical network and evaluated simultaneously. This is different than in Simulink, where these blocks would be evaluated explicitly or one after the other. We have a spring in our valve that acts to center the spool. We could have modeled this spring using the translational spring from the Foundation library. However, we chose to create a custom spring using the Simscape language that takes the stiffness as a lookup table. In the next portion of our presentation, we'll show how we created this component using the Simscape language. In this demonstration, we're going to see how we can model custom physical components using Simscape language. We wish to create a model of a spring whose stiffness is nonlinear. We're going to create this spring using the Simscape language. The component we create will look like this. You can see it has two physical ports representing the two mechanical connections for the spring. Here is a portion of the Simscape language source code, and you can see we have defined the stiffness using a lookup table. In looking at the code, we will see that the Simscape language is MATLAB based, it's object-oriented for reuse, and can be used to define implicit equations, DAEs and ODEs. Here is a Simscape model that compares the behavior of a linear spring from the Foundation library to a custom spring where the stiffness is defined as a lookup table. Looking at the parameters, we can see a single value for the spring rate in the Foundation library spring and a lookup table where the stiffness varies with the displacement. Between the displacement of 0 and 0.4 millimeters, the stiffnesses are the same. Beyond 0.4 millimeters, the custom spring stiffness increases by a factor of 5. When we run the simulation, we can see how the springs behave. Each spring is subjected to the same input force at 1 second, and we can see that at deflections above 0.4 millimeters, the spring behavior differs. If we double-click on the spring and click on the source code link, we can see the Simscape language source code that is used to define this component, including parameters, variables, and the equations themselves. We'll go through the Simscape language source code in more detail so that you can see how the component is defined. Here's the source code that defines our nonlinear spring. Our nonlinear spring component has two mechanical physical ports. Those are defined here. We reuse the domain definitions provided by Simscape for the mechanical domain. This makes sure that our Simscape component is compatible with the rest of the translational mechanical components in the Foundation library. We could have also defined our own new physical domain if that were necessary for our system. We also use this file to define the user interface. Here you can see the parameters that we wish to enable users to modify. Those are defined here. In the Simscape language source code, we define the parameters, the units, the default values, and the prompt that the user sees in order to define those values. In the next section, we leverage MATLAB. Here we use MATLAB to verify that a parameter value is within a legitimate range. You can use MATLAB functions and expressions for typical physical modeling tasks, such as analyzing parameters as we've done here, and for performing preliminary computations. In the next section, we define how this component behaves. We wanted to make sure that our spring had a nonlinear stiffness based on its deflection. Here is the Simscape language source code that defines that. There are some important aspects about the equations section. The equations that you see here are based on variables, their time derivatives, parameters, and other quantities. The key difference is that these are simultaneous equations. All of the equations that you see here will be evaluated simultaneously, not sequentially or one after the other, as you are used to in MATLAB. These equations can be DAEs and ODEs. Another key thing to remember is that assignment is not required. Again, because all of these equations are solved simultaneously, it isn't as if we are using this equation to find x, and then once we have that value, we use it to find f. All of these equations will be evaluated at the same time as they would be in a physical system. This is much different than input-output languages that you may be familiar with, such as MATLAB, Simulink, and pure C code. In this demonstration, we have seen how to use Simscape language to model a custom physical component. Now that we've seen how to build models using components from the Simscape Foundation library and Simscape language, we'll see how we can enhance the model using components from the Simscape add-on products. We'll also see how the Simscape editing mode lets us share these models with users who have not purchased licenses for the add-on products. Our model of the hydraulic lift has all of the components that we need. We can enhance the model further using Simscape add-on libraries. The Simscape add-on libraries include advanced components and effects. The blocks are more comprehensive. A single block can represent an entire four-way directional valve. The blocks also include additional parameterization options. This makes it easier for you to assign accurate parameter values based on datasheets or other sources of information you may have. The blocks also include additional physical effects. This includes friction losses, thermal dependency, and other effects found in physical systems. And using the add-on libraries, you can also do multi-body simulation. I'll now switch over to the model to show you some examples. In our model of the hydraulic lift, we have modeled each of the physical components by assembling blocks from the Simscape Foundation library. In our model of the four-way directional valve, we have modeled the path for the hydraulic fluid from the pump to the A and B ports and back to the tank using variable area orifices. And we have converted the motion of the spool to the area of these orifices using physical signal library blocks. This would have been much easier had we used the add-on library Simscape Fluids. In Simscape Fluids, there's an entire valve library dedicated toward the modeling of directional valves. This entire set of blocks could have been replaced by a single four-way directional valve block. We'll go to the top level of the model, and using a MATLAB command, we will override the variant and use a standard block from Simscape Fluids. Now when we go in here, we can see that the standard variant is active where we have used a four-way directional valve. When we click on it, you can see the different parameterization options. These options make it easy for us to assign accurate parameter values no matter which datasheet we're using, or if we only have measured data. Let's take a look at the hydraulic actuator. Our double-acting hydraulic cylinder has been modeled using variable volume chambers from the Simscape Foundation library. In Simscape Fluids, there's an entire library dedicated towards modeling hydraulic actuators, including a double-acting hydraulic cylinder. So we can go back to our model and use a MATLAB command to enable the other variant, which uses the double-acting hydraulic cylinder from the Simscape Fluids library. The same applies to electrical and mechanical systems. If we look at our model of the DC motor, we used electrical and mechanical components from the Simscape Foundation library to model the electrical circuit, the mechanical system, as well as the gear model. If we look in the add-on library for Simscape Electronics, we can see there's an entire library of motor models that we could have used. In the Simscape Driveline add-on product, there's an entire library of gears that has additional effects. So we'll go to the top level of this model, activate the other variant, and now we'll see that we have used a DC motor model from Simscape Electronics that has additional parameterization options and effects. Similarly, we've used a rack and pinion block from Simscape Driveline, which allows us to easily include friction losses into our system. Finally, we'll take a look at three-dimensional mechanical modeling. Modeling the load in Simscape, we have simply used a mass, a force due to gravity, and a translational damper. We could create a much more accurate model of the scissor jack using Simscape Multibody. Here we can model solids, joints, and other types of constraints to create a three-dimensional mechanical model. Going to the top level, we'll activate the other variant, and when we go into here, we can see that now our scissor lift is modeled using different parts that we have assembled together, and joints that define how those parts move with respect to one another. This Simscape Multibody model also creates for us a three-dimensional animation of our scissor jack connected to the rest of the system. So in this example, we have seen how we can enhance each of the components using blocks from the add-on libraries. The one add-on library we haven't used yet in our model is Simscape Power Systems. Simscape Power Systems has more advanced components in the electrical area for modeling three-phase mechanical machines and generators, as well as simplified models of semiconductors and power transmission devices. Here is a summary of the modeling capabilities in Simscape and its add-on products. The Simscape platform has libraries in a number of different physical domains, and you can add your own custom domains and components using Simscape language. In the Simscape add-on products, you will find more advanced components and capabilities such as three-dimensional modeling and animation in Simscape Multibody and a range of analysis tools in Simscape Power Systems. Simscape enables you to take full advantage of the advanced capabilities in the Simscape add-on products without purchasing the full set of licenses. You can share models with other Simscape users. They can run simulations, analyze results, and generate code from models that include the Simscape add-on products, even if they haven't purchased licenses for those Simscape add-on products. Your model developers produce models that use Simscape and the add-on products. When those models are saved in restricted mode, they can be shared with other Simscape users who have the add-on products installed, even if they haven't purchased the additional Simscape add-on licenses. This table summarizes the capabilities that one has in full mode or in restricted mode, and your model users who are working in restricted mode can still access quite a bit of capability, including changing numerical parameters in Simscape and Simscape add-on libraries, accessing the Power GUI in Simscape Power Systems, and viewing 3D animations in the Mechanics Explorer of Simscape Multibody. You can also generate code for hardware in the loop and other use cases. There's still quite a bit of functionality that can be accessed in restricted mode. In this demonstration, we're going to see how we can share models using Simscape editing modes. I have a model developer who has created a model using Simscape and Simscape add-on products. He needs to share this model with model users, who need to use this for various simulation tasks. However, the model users do not have access to licenses for the Simscape add-on products. We're going to make it possible for the model users to use this model by sharing the model in restricted mode. Models that are opened in restricted mode do not require licenses of the Simscape add-on products. However, model users can still do many standard tasks, such as run simulations, change parameter values, and generate C code. I'll now switch over to the model so you can see how this is done. To show you how this capability works, we're going to show this in two separate MATLAB sessions. One MATLAB session for the MATLAB developer, who has a license for Simscape and all of the add-on products. We'll use a separate MATLAB session for the model user, who will only have a license for the Simscape platform. Here's our model of the hydraulic lift. It uses many of the Simscape add-on products, including Simscape Multibody for three-dimensional mechanical simulation, Simscape Fluids for the hydraulic network, which includes hydraulic actuators and valves, Simscape Driveline for gears and other components, and Simscape Electronics and Simscape Power Systems for the electrical system. In full mode, we have access to all of the capabilities in Simscape. This means we are able to run the simulation, see the animation of the results in the Mechanics Explorer from Simscape Multibody, and we can also make structural changes to the model. For example, if I go into our model of the servo motor, I can delete blocks and make other structural changes. Now the model developer is satisfied with this model and wishes to share it with the model users. So I'll close this model and now switch over to the session of the model user, who again only has a license for the Simscape platform. This is the same model that the model developer was working with, but we can see in the diagnostics that the model has been opened in restricted mode because licenses could not be obtained for the add-on products. In restricted mode, some operations are not permitted. For example, if I want to go into the servo motor and try and delete the damping, I get a message saying that making structural changes to the model, such as removing blocks, is not permitted. However, I can do many of the other operations that a model user would like to do. For example, I can run the simulation. I still have access to the 3D animation from Simscape Multibody, and if I look at the plot on the scope, I can see the numerical results. I'm also permitted to change numerical parameters. If I go into the control circuit, I can change the gain, I can change the value of a resistor, so effectively changing the gain on the amplifier, and I can rerun the simulation and see how the behavior is changed. So even in restricted mode, there are still quite a few valuable tasks that I can perform as the model user. In this demonstration, we have seen how we can share models using Simscape editing modes. Now that we have seen how to build and enhance the model, we'll take a look at logging simulation data for analysis and for detecting the causes of slow simulation. In this demonstration, we're going to see how to log Simscape simulation results to MATLAB. We have a model of a hydraulic jack. There are many simulation results that we wish to analyze and post-process. To make that easy, we're going to log those results to MATLAB using Simscape logging. When Simscape logging is enabled, a data structure is created in the MATLAB workspace whose structure matches the hierarchy of the model. We can use MATLAB commands to go through that hierarchy to create plots, and we can use the Simscape Results Explorer to further investigate that data. Here is our model of a hydraulic lift. We wish to investigate the simulation results of our Simscape model. The easiest way to do that is to enable Simscape logging. If I go to the configuration panel and select the Simscape pane, I can enable Simscape to record all of the simulation results to a variable in the MATLAB workspace. We'll run the simulation and investigate the results. Now that the simulation is complete, I can right-click on any block in the Simscape network and select View Simulation Data. This opens up the Simscape Results Explorer. Here I can see the flow rate from the pump. I can also take a look at the pressures inside the actuator. If I go to the double-acting hydraulic actuator, I can select the pressure for the A side and the B side. If I wish to overlay these results, I can simply select that here. Simscape logging results also include data from Simscape Multibody. If I go into the scissor lift and click on the prismatic joint inside the actuator, I can see the position, the velocity, and the acceleration of that joint. If I would like to go to that block itself, I can simply click on this hyperlink and I will be brought directly to the place in the model where this data was created. In this demonstration, we have seen how we can log the results of a Simscape simulation to the MATLAB workspace. In this demonstration, we're going to show how you can find the cause of a slow simulation. We have a model of a hydraulic jack. When we run the simulation, we notice that at certain points the simulation runs quite slowly. Here at about 4 seconds it goes quite slow, and again at 10 seconds the simulation goes quite slow. We know that there are elements in our model that are causing it to take small steps, again resulting in slow simulation. We're having trouble finding them. We're going to see how we can use the solver profiler to locate problems in our model. The solver profiler can show us different aspects about the step size when zero crossings are generated and other aspects of the solver performance. Using these, we can identify elements causing slow simulations and fix the model so that it runs smoothly. Here is our model of a hydraulic lift. When we run the simulation, we see that it stalls near 4 seconds and then it starts running very slowly again later on at around 10 seconds. We know there's something in our model causing it to run slowly. To find it, we'll use the Simulink solver profiler. To access the solver profiler, you click on the link in the lower right hand corner that talks about the solver, and here's where you can access the solver profiler. The solver profiler collects information during the simulation that can help you find problems with your model. We will enable logging of continuous states and Simscape states, which will also log Simscape zero crossing statistics. We will now rerun the simulation, collecting those statistics. You can see the simulation progress in the lower right hand corner. Because of all the information that it is logging, the simulation will take slightly longer. At the conclusion of the simulation, the statistics that have been collected are shown to us. There are some suggestions that have been made to us in this tab, and it identifies the two ranges of simulation time where we notice the model running slowly. It identifies solver exceptions and zero crossings in these ranges. If we click on the zero crossing tab, we can see a set of the blocks that generated zero crossings. And we can see that one of these blocks generated most of the zero crossings. And those zero crossings occurred right during the periods of time we noticed the model running slowly. If we click on highlight to block, it will take us directly to the block that's generating those zero crossings. When we come in here, we can see the parameter settings. We can see that the stiffness and the damping in this hard stop are quite far apart from each other. These would be likely parameters for us to change in order to improve the simulation of the model. By decreasing the stiffness and increasing the damping, we should be able to have the model run more smoothly. I'm now going to rerun the simulation using the solver profiler, and we can see the change in the behavior with the number of zero crossings that were created. The simulation is complete. We can see that far fewer zero crossings were created. That's visible both in the plot and in the table. And if we go back to our simulation results, we can see that the results look quite good. If I rerun the simulation from here, we can see how quickly it runs. In this demonstration, we have seen how we can use the Simulink solver profiler to find the cause of a slow simulation. Now that we have our model running quite well on the desktop, we will see how we can configure the model to simulate in real time. In this demonstration, we're going to see how we can configure a hydraulic lift model for hardware-in-the-loop testing. We have a model of a hydraulic lift, and we are happy with the results we get from desktop simulation with a variable step solver. We now need to configure this model for hardware-in-the-loop testing. The challenge here is that portions of our model are numerically stiff. We'll need to use the Simscape local solver in order to make this model real-time capable. Here are the steps that we'll go through. First, we'll configure the model to use a fixed-step, fixed-cost solver appropriate for hardware-in-the-loop testing. We'll then rerun the simulation on our desktop computer and verify the results of that simulation match our reference results. We'll then generate C code from the model and download it to the real-time hardware. We will rerun the model on the real-time hardware and verify that we get no overruns, that the simulation is running fast enough. Next, we will change a value in one of the Simscape blocks on the real-time target and then rerun the model on the real-time target. I'll now switch over to the model so you can see how this is done. Here is the model that we're working with. A hydraulic cylinder extends and contracts to raise and lower a load on a scissor jack. When we look at the three-dimensional animation produced by Simscape Multibody, we can see how the system behaves. This cylinder extends and contracts to raise and lower the load. If we look at this scope, we can see that the system is tracking our reference signal quite well. Since we're happy with the results from our desktop simulation, we now wish to configure this for hardware in the loop simulation. The challenging part is that some of this model is numerically stiff. We have hydraulic actuators from Simscape Fluids, and we have electrical models from Simscape Electronics, and mechanical models from Simscape Driveline. In order to go through this process, we'll use a MATLAB script. Our first step is to get a set of reference results. We will rerun the model with the variable step solver ODE23T, save the results, and plot them on a figure window. So here we can see our simulation results. Next, we will use these MATLAB commands to configure the solvers and rerun the simulation. You can see we are using global fixed step solver ODE3, and we have enabled the Simscape local solver. Now we will take these results and overlay them on the original set of reference results. And when we zoom in on the results, we can see that the results from the variable step simulation and the fixed step simulation match extremely well. If we go into the model, we can see where we have enabled the Simscape local solver. Here we have enabled the local solver, made our selection, and picked a sample time, and we have also enabled fixed cost simulation. This limits the amount of computations per time step, ensuring that we will avoid overruns on the real-time system. If we look at the MATLAB command window, we can see that our simulation is running much faster than real-time on the desktop, and that's a good indication that it will run fast enough on the real-time machine. Now that we are happy with the solver settings we have chosen and the speed, we're going to pick a parameter that we can tune on the real-time target. The parameter that we are going to tune is the damping in the motor. The damping in the motor might be something that changes with age, something that would be difficult to do on real hardware, but we can change this parameter quite easily in the model and then test how the controller behaves with an older motor. We have configured this to be a runtime parameter. That means we will be able to vary the numerical value on the real-time target and rerun simulations without regenerating source code. At this point, we will now generate the C code from our model. This is using the command slbuild from Simulink Coder. Here you can see the messages being generated as the model is converted to C code. Once the conversion is complete, we will download it to this real-time target, which is running Simulink real-time, and we will be able to view the results of the simulation on the real-time target using this monitor. We'll also be able to monitor the progress of the simulation in Simulink on this scope, running in external mode. So now we can see that the model has downloaded. We will set up our model to be run in external mode, again giving us the ability to monitor the progress here. We will then connect to the target and run. So now the simulation is running on the real-time target. You can see the results of the simulation on the monitor, and they are synchronized with the results on the scope. At the conclusion of this 20-second simulation, we will upload the results from the real-time target and add it to the plot where we are comparing simulation results. So we can see that the simulation is complete. We didn't have any overruns, which means that our simulation is running fast enough, and we can see that the results from the real-time target match the results from our desktop simulation exactly. So now we have a model that is accurate and runs very quickly. We can use this model in hardware in the loop testing, where we test how the embedded software and hardware behave as we change parameters in the physical system. The parameter we're going to change is the motor damping. So the original value was 0.01, and we have changed it to a value of 0.2. We did that using MATLAB commands. We'll now rerun the simulation simply using the command tg.start. You can see that we are running the simulation on the real-time hardware, and you can hopefully see that the two lines don't line up quite as well. This is the effect of the aged motor that we are testing in our system. At the end of our 20-second test, we will upload the results. Our test is complete. We can now upload those results, And when we look at our plot of all the simulation results, we can see that our modified lift with the extra damping in the motor is behaving much differently. We would have the ability to test how our embedded hardware and software behave with this modified physical system. In this demonstration, we have seen how we can configure a Simscape model to run on hardware-in-the-loop testing. In this presentation, we have seen that Simscape enables you to use physical networks to model systems spanning multiple physical domains. You can create custom components using a MATLAB-based language, and models that you create using the Simscape add-on products can be used without requiring extra licenses of those add-on products. That concludes our presentation. We would like to take some time to answer your questions. Please enter them into the window. We will be back in a moment to answer them.